you have chlorine in the cyclohexane. That's where we start. You're still going to have a chlorine there, but somehow you got the OH next to chlorine. And that is a key to solve this problem. I know I've been telling you the organic chemistry, that memorization is not needed, but some amount of memorization is still needed. You got to know when halogen and OH in the bisphenols position, that is a product of the haloform reaction, especially when they are trans relationship. If you got the chlorine and OH on the same side, that is not the product of the haloform reaction. Haloform reaction should have a halogen OH and right next to each other and gotta be trans, like this. Once you recognize that, then you may think that this is a product of the haloform reactions. And then in order to do this, you need double bonds. So this can be created from this chlorine ion. Water makes an attack in the backside. This goes up, then you can get that. And then chlorine ion can be made from double bonds. And then how the double bond is going to be created? Created from this alkyl halide, chloride. We need to make a double bonds here. So I'm using Berkey base because I don't want SN2 reaction competing with it. So Berkey base will make an E2 elimination reaction exclusively. It makes a double bond by abstracting proton, making double bonds, kicking the halides out. You get this. Then you are doing chlorine in water. That makes a chlorine ion, opened by the water, it makes this. So this is kind of a thinking process that you have to do. You first have to recognize what is the product, what can be formed with, and then you have to find that intermediate to get there, and then you need to connect that from the starting material to the multiple reaction steps. And then this is kind of the things that you need to do. And then it'll be good to use a number because you're not adding all the reagents at the same time. You're treating the molecule with a strong base first. That's why number one makes these E2 elimination reactions. Then step two is doing haloform reaction, chlorine in water. So that is kind of what is need to be done to solve problem.
Is it appropriate to say for step two, you take the strongest nucleophile to perform the haloform reaction? Like, you know how in step one we formed the halide ions, the halogenation reaction, we formed the halide ion. Then you mentioned how if it's the water and cyanide, we use cyanide instead, right?
Because the cyanides are very strong when you combine them.
Yes, so exactly. So that's step two. Is it appropriate to say we take the strongest nucleophile percent?
Well, it depends on what you want to do. In this case, you didn't have OH there, so that's the reason why water is good enough. It depends on what step. All right, the next one. It's pretty similar. Now you recognize the pattern here. It's an OH and Cl trans relationship right next to each other. That looks like the products of the haloform reaction, right? But also has to be OH has to be on the more substitutive side, and then chlorine has to be on the less substitutive side to become a haloform product. Biochemistry also critical, I mean the stereochemistry. If somehow you got the chlorine here, OH there, you cannot make that the haloform reaction because the antimicrobial products, and when the haloform reactions doesn't make an antimicrobial product. So you really have to analyze things very carefully. Everything must be right. So, at least at this one, OH is a nucleophile sitting on the more substitutive side, chlorine electrophile sitting on the less substitutive side. They are opposite to each other. That means these things are made from the haloform reactions. The chlorine ions are made like this, and then more substitutive carbon will become more partial carbocation. And this partial carbocation is going to be attacked by the water, and that opens it up, so you get the chlorine here. Some of you may be wondering, the methyl was at the dashes, how come this becomes a wedge? How come that becomes a dash to a wedge? Because the nucleophilic attack involved inversion of the stereochemistry. Things that you learned from SN2 still applies. Water making as a nucleophile, it makes an attack from the backside. So this methyl group has to switch the side, like in SN2 reactions. So that's the reason this method in the behind will move to the full front side after the nucleophilic attack by the water. Anyway, so this is coming from that double bonds. These double bonds, you treat the chlorine water, then you can make that. Then you have to make this double bond from this. So previously you thought that, oh yeah, sure, we can use a TP oxide and make H elimination reactions. Is it right? Can you do this? It was only yesterday we took test 2. Don't tell me that you already forgot. This is not possible because that's the alcohol, not the halide. You see the difference is, previous one was a chloride, so we can make elimination reactions. But this we start from the alcohol, so you cannot do the H elimination reaction. What needs to be done? You instead of base, you just have to treat acid. OH get protonated, then water goes out, then carbocation forms, then you get the E1 elimination reactions, so you get this. So this is how things are connected from the all part still. So you still have to understand all the things that we have discussed.